Hi everyone, welcome to Think Then Code. Today we'll be solving the problem divided nodes into maximum number of group. This question appeared as the fourth problem in the recent weekly contest, so let's solve it. You are given a positive integer n representing the number of nodes in an undirected graph. The nodes are labeled from 1 to n instead of 0 to n minus 1. You are basically given 2D integer edges, so we are given edges that indicates a bidirectional edge between the nodes. Okay. So notice that the graph may be disconnected. Okay, so it can be a forest. Divide the nodes into m group which are one indexed such that each node in the graph belongs to exactly one group, and for every pair of nodes in the graph that are connected by an edge ai belong to group with index x and bi belong to group with index y such that y minus x is equals to 1. Okay, and return the maximum number of groups, that is maximum m, into which you can divide the nodes, and return minus 1 if possible. So let's try to understand the question. What the question is saying is we are given the edges, and from the edges we create this graph. So let's assume this is the graph. So what question is saying is we have to divide all the nodes of the graph in some groups. So all the nodes go into some groups, and this group should have following property. The property is that let's assume this node belongs to second group. So all other connected nodes, that is this node which is connected to this and this node which is connected to this, should belong to a group such that their absolute difference is 1, which means if this belongs to group 2, this can belong to group 1 or group 3. In the same way, this node which is connected to the node in the group 2, this can belong to group 1 or group 3. Why? Because 1 minus 2 absolute will give us 1, and also 1 uh, 2 minus, sorry, yeah, 1 minus 2 and 2 minus 3 absolute will also give us 1. That's why here we can only accommodate 1 or 3. Next question is saying is we have to maximize this count of groups. That is, we first have to assign every node to a group, and then we have to maximize this count of groups. That's the question. Let's see the test case. What the test case says is we are given 6 vertices and its edges. We make the graph and the answer is 4, because in this way all the nodes can be assigned to groups and no directly connected nodes belong to groups such that this condition violates. Means the directly connected nodes only belong to adjacent groups. That's it. Let's see the constraints. The number of vertices can be 500 and the edge count can be 10 to the power 4. Okay. Understand the intuition behind the approach of this problem. If we see this test case, that there are 4 groups. These 4 groups are basically the levels of BFS. If you just see, this is basically a BFS starting from node 5. So we are starting from node 5 going to adjacent, that is node 1, then we are going to its connected, that is 2 and 4, and then connected to 2 and 4, that is 3 and 6. So basically this is a type of a BFS which are starting from node 5. So the same BFS I have replicated it here. We are starting from 5, 1, 2, 4 and 3, 6. So in this there are 4 groups. 5 is one group, this 1 is second, 2 and 4 is third, and 3 and 6 is fourth. And these groups are basically the levels of BFS, which means the 5 is at the first level, 1 is at second level, 2 and 4 at third level, and 3 and 6 are at fourth level. So what if we start our BFS from node 1? If we start our BFS from node 1, then we go to adjacent of node 1, that is 2, 4 and 5, and then to adjacent of 2 and 4, that is 3, 6. In this we are only getting 3 levels, or we say only 3 groups can be formed. And if we see the another BFS which we start from node 6, In node 6, if we go to the adjacent of node 6, that is 2 and 4, then we do the BFS. In this way, again 4 levels are there. That is, our BFS have 4 levels. So basically what I am trying to convey is, if you start your BFS from different nodes, you can have different levels or different count of groups. And actually that levels or that count of groups is basically the answer. So basically what we will do is, we will start from each node of the graph, do the BFS from that node, entire BFS, and get the level. And we will maximize the count of level by doing BFS from each node. The next thing is, we can also have connected components in this problem. So basically, if this is one graph, there can be another component of this graph which is not connected to it properly. And this is basically a very simple thing. Why? Because we can get answer for this graph the same way we can do BFS. The same answer can be for this graph, and these two answers can be added to get the final answer. Why? Because basically we have to just maximize the groups. So if we just add the groups, that will give the maximum number of answer, that is maximum count of groups. So let's understand the algorithm with the dry run. What we are doing is, we are starting BFS from each node, and we are storing what the groups will be. So let's understand when the answer will be -1 and when we can get the possible answer. So if we are starting our BFS with 1, so let's assume this is our queue. We add 1 to our queue, and we add also -1. Why we are adding -1? Because we want to do a level wise BFS instead of just a simple BFS. Now after adding, we also assign the current group of that node to it. So we assign 1, which is the current group, to our node 1. Now we go into the while loop, we remove 1, and we go to the adjacent of 1. So adjacent of 1 are 2 and 3. So we assign the group, we assign the current group, we assign the next group to them. So next group is 2, so we assign the next group to them and add them to the queue, that is 2 and 3. And since we encounter -1 here, we remove -1 from here and add it to the end of the queue again. Next, we are doing the BFS for this level. So in this level, we will go to adjacent of 3, that is 5. We assigned it group, so we assigned it group 3, and the same way 2 is connected to 4, we assign it group 3, and we add 4 and 5 to our queue, and this -1 is removed from the queue and it is added at the end. Now here comes the part. Since we are at 4, we first remove 4 from the queue, and if we check the adjacent of the 4, the adjacent of 4 are 2 and 5. And whenever we are picking these nodes, we are also checking that if the groups are filled, for example this is groups is filled and here also groups are filled, do that satisfy the condition of which is given in the question. For example, if U and V are connected, then the absolute of the group of U minus the group of V this should be equal to 1. So their absolute difference should be equal to 1. So if we see 4 is connected to 5 and 3 and 3 are not giving us absolute difference of 1, it is giving absolute difference of 0. So in this case we return -1. We stop our BFS and we completely return -1, which means that this graph cannot be broken into the groups. So this is one thing. Let's try it with a different graph. Let's assume this is the graph and we start our BFS from node 1 again. So we have the queue, we added 1 to our queue and we added -1 to our queue, and we assign the current group of 1 as 1. Then we traverse to its adjacent. So we remove 1, add 2 and 3 to our queue, assign them the next group, that is 2, remove -1, add -1 to it. Now we will process this level, that is the level of 2 and 3. We remove 2 and 3, go to its adjacent, that is 4. We add 3 here because it's adjacent. We have to give the next group, and the adjacent of 3 is 5. We also give it the group 3. And if we see, we remove 2 and 3 from it, and the adjacent of 2 and 3, which were already filled at that time, was only 1, and this 1 is having an absolute difference of 1. So we don't trigger into the situation which we triggered earlier. Now 2 and 3 are removed. We add 4 and 5 to our queue, and this -1 is being removed and it is added here. Now we process 4 and 5. We again check, since 4 is connected to 2 and 3, does this violate the condition of the question? That is, directly connected nodes should have absolute difference of their group to be 1. So 3 and 2 having absolute difference of 1, that is okay, and 2 and 3 again absolute difference of 1, it is okay. And it's the same case for 3 and 5. Their absolute difference is also 1. So this doesn't violate our condition, and we do the BFS, remove 4 and 5 and add 6 to our BFS, and also assign the group of 4 to it. And this -1 goes here. And finally, after removing 6, the BFS get completed, and our answer is the highest group which we have assigned, that is 4. So this is our final answer for this BFS. If we start our BFS from 1, the answer can be higher if we start our BFS from any other node. But if we start our BFS from 1, then 4 will be the answer. And in this way, we will do the BFS from each node. We will do first from 1 to 2, then 3 and 4 and 5 and 6. And this algorithm applies and gets what's the maximum number of group you have assigned. And if there is a connected component, for example, this is first component of it, and this can be the second component. So we get answers from both components and add them. And why we are adding them? Because we want to maximize our group. So instead of putting them in the same group, we just create different groups, new groups, to maximize the count of these groups, because that's what question wants. I hope you understand the approach. Now let's look at the code. So this is the accepted code. So basically in our code, first we are creating an adjacent matrix, adjacency list, and then we are creating this vector of vector for components. Basically in this we are storing all the components. I will explain this further in the question. So what we are doing in our main function is, first we are clearing our adjacency list and clearing all the components. Then we resize our adjacency list to n+1 so that it can accommodate all the nodes. Then here we are just filling our adjacency list. Here we are filling the components. So what we are doing here is, let's assume this is the graph. This is 1, this is 2, and this is 3. And this is here is 4, and this is here is 5. So what we are doing in this fill components is, we are basically creating vectors. So we are creating, this is one vector, this is second vector, and in this vector we are adding the nodes of the components. So these are two arrays, or you can say two vectors, and these two vectors contains the nodes of all nodes which are in this single connected component. For example, 1, 2, 3, all the 1, 2, 3 which are single connected component are added to this vector, and since 4 and 5 is another component, this 4 is 5 and added at another vector. And then we have answer, which is the final answer which will be returned. And this is the component answer. Since the graph can be disconnected as it is given in the question, we are storing each component's answer 1, 2, 3, 4, 5 as these are 2 components. Each component answer is in this variable. Let's understand how this fill components function is working. So what we are doing is we are creating a temporary vector to add in our vector of vector components which we are having here. And what we do here is we create a visited array and we traverse nodes from 1 to n. And if that node is not visited, we start a DFS from that node and add all the components in that vector. And this is basically the DFS, which is adding components, adding the nodes of the components to our components vector. Now what we are doing next is we are considering every component in our components vector. For every component, we are considering every node in that component. Yes, for every component, we are considering every node in that component. And for every node, we are maximizing the component answer by doing a BFS starting from that node. So basically for every component, in that component, we are starting a BFS from each and every node in that. And if the component answer is -1, we return -1 because that component cannot be framed into groups. And if it doesn't return -1, means that BFS doesn't return -1, we add that answer to our final answer. And then we return our final answer. So let's see how the BFS is working here. So in the BFS, first we are creating our queue. Since the BFS is starting from U node, we push U node into it and then we push -1 because we are using a level wise BFS. Then we create a vector of groups. This vector stores which node belongs to which group. And then we have a current group variable which store what the current group which we are filling. And since we have already filled our U node from which we have started, so we fill the group array for U node to our current group, that is 1. And this is basically the BFS. So we increment the current group as we are going in the next level of the BFS. We loop until we don't get -1 in our queue because we are using a level wise BFS here. We get the front of the queue, we pop it, we see all its adjacent here, and if its adjacent is already filled, we check whether the filled adjacent and the current node is their absolute difference is 1 or not. If it is not 1, we return -1, and if it is not filled, that the adjacent node is not filled, we push it into queue and assign its group to the current group. And when this level wise BFS is completed, we pop from it. This pop is basically for removing -1 from the front, and then we add -1 to the back. And then we finally return answer. We are doing current group minus. Why? Because let's assume our current group is 1. We filled for it, then our current group is 2. We filled for it, then our current group is 3. We filled for it, but now our current group is 4, but we are not filling anything here. We are just removing from the queue. So basically, we have not assigned this group to any node in our graph. That's why we are doing a decrement here, and finally we return the current group, that is the maximum group we have assigned to any node. So that's all about the code. Let us understand the time complexity of this. So basically what we are doing in our code is we are performing BFS, and we are performing the BFS n times through every node. So n here is the number of vertices in a graph, and we are doing BFS through every vertices. The complexity of BFS is n plus e, where n is the number of vertices and e is the count of edges. So that is becomes big of n into n plus e. And the space complexity is big of n plus e because this is the space which will be taken by adjacency list approach. So I hope you understand the video. If you have any doubts, then do comment down. I will try to resolve them. And like this video and subscribe. Hope to see you in the next video.